battery or a USB cable connected to a power supply. Okay, good. So, and now, David, I also record my screen here because the German students complain that they can't read the display.
Yeah.
So I'm recording my screen as well here.
Oh.
And then we can put both of those recordings up on the website.
So this that are going to record?
No. This one you definitely have to record.
Oh.
We just record this one as well. Just check. And so Philip went home then?
Yes.
Yeah. Okay, good. Then let's talk about the assignment for, actually that's a couple of minutes. So let's do some programming for the next 20, 30 minutes, and then we'll talk about the assignment, because at that time some of the students may join us. Okay. So, I did post the assignment. I'm already actually my students and I on Thursday we took our humanoid robot to the real rock climbing gym for the first time, which was kind of, for me at least, very exciting and pretty cool. We didn't do any motion planning or motions, but we tested basically static positions and holds to make sure that the robot can actually stay on the wall and what kind of reach he would have. It actually looks like he would be able to at least have the reach to climb the um, simple routes like the white one. You said you did some rock climbing, right?
Yes.
Yeah. So is it the same in Germany? I think Germany they may write the numbers down or something.
I think it depends, but yeah, they are pretty much the same.
So if you haven't done rock climbing, this is kind of what the wall would look like. And then you have the different holes. And the different routes are color coded. So all the yellow ones belong together in the simplest way. There's some variations, but here all the yellow ones belong together. Your hands have to start here where the tape is. So at the bottom there's a tape, and then you have to climb to the top of the tape of the same color using only the yellow holes. And then the tape gives you the difficulty level. So in this gym, and I think everywhere in Taiwan, but I'm not sure about that. But anyway, in this gym, the simplest one is the white one. That's like V beginner. Then the first real climbing one is the yellow one, which would be a V1. Then the green one, the green tape here, V2. And then V3 is pink. And then V4 is blue. And then after that, I can possibly climb it, so I haven't looked into the colors yet. So that's what we want our robot to be able to do and work on. So here the pink one, the blue one. You can see the holes are getting more difficult because they get smaller. So the first part of the project is to basically take a picture of the wall and extract the holes that you need to climb through, right? That you can do in the assignment. I specify that we will give you a cropped part of the picture, so not the entire route, but just the cropped part. And then you can use that in order to calibrate your vision systems. So you can click on what you think is yellow. And we'll tell you what color, so you don't need to read the tape or anything like that. You can actually ignore those. and But you want to extract the information from these holes that are important to you for your climbing robot. Now, that means the output of your, I mean, you can see in general that's a non-trivial problem. If you look at all of these holes, for example, then here you, based on experience, because I've seen these kind of holes before, how would you graph this? Yeah. So it's basically like at a little bit of an angle and you would grab it from the top, right? And most of these are like that. This one here you would grab, this one here you would grab. But then the purple ones, or not purple, the cyan, light green ones. These ones you can also grab like that, and you can actually grab them from any direction, right? But there are other ones that are different. How about this one? Oh, okay. I think this is impossible to hold. I think this is a foothold. Yeah. It's probably for the feet, but you're right. Maybe you can pinch it, but then you'd have to be really strong pincher, like the kind of guys that crash billiard balls or something like that on that level. This one here similarly. So I think it's a little bit much for the vision system to figure out what kind of hold that is. So I think we will give it the general outline. And then, how about this one actually? How do you hold this one? Oh, no, I don't think so. Maybe, but I don't think so. What did you had it right? I think. I would say this. Like pin? No, I think it's actually under. Oh. Like you actually grab it like this. I don't think you can grab it very well from the top. So you pull it from the bottom. Yeah. And that is a really hard problem. Even human climbers often have to go and look at them very carefully from below before. Not these ones. These ones are pretty standardized, but there's other ones for the more difficult routes that they think you need to grab one way, and then it turns out you need to grab a totally different way. And I was actually, I mean, one of my students, he started climbing with us, and he was he's from Brazil, and now he just loves rock climbing. So he's very good. He's the best rock climber in my lab. And we went climbing once, and they do play tricks on you. So what it looked like was two of these. And this was for the competition, some kind of competition routes that they had set. So I didn't join the competition because I'm not anywhere nearly good enough. But this one was the fun one, which was supposed to be the easiest one. And it basically looked like that. No, wait, the other way around. So when you look at that, you think it's pretty straightforward. Here are your arms, your head, torso, and here are your legs, right? And then the next thing was here, a big kind of thing there. And I'm sure, like I'm not a good climber, but I'm sure everybody that looked at that route would think this is how you started, right? But the problem is this part here was full of, and you don't, and then you think, oh, I'm there, then I can go there. It's actually not too bad, right? Like I can pull along here. Once I'm here, then my next move would be something like this. Right? But when you tried it, you realized this part here was all made out of plastic. So there was no friction at all. So it's completely impossible to stand on it or have any kind of hold on this. So then nobody figured it out, but my student, he's the only one that managed to do it. And the way that you had to start this climb was like this. And you had your legs up there. And this, nobody would have thought of this beforehand, right? And then it just got more crazy from that. So even for humans, it's very difficult to figure out the exact holes just from a picture. Often you have to climb there or try it out first. So we will simplify that and we will use only a limited number of holes. And then we don't, I mean, yes, maybe next year we can do that kind of climb. That would be amazing. But we'll start more realistically. Still, it'll be exciting. The other thing that we realized is for climbing the higher levels, here you see these wooden ones that don't actually belong to any route. Here there's a bunch of wooden ones. Here's a bunch of wooden ones. So they're not actually part of any color. And they're much smaller. And then you only sort of go left and right there, not up with them. Do they have those in Germany as well? Yeah, so you just go left and right. They don't really belong to any route, but they're just there to practice your finger strength. It's kind of like doing pull-ups or something like that. So no route there. And they're significantly smaller. And that's what makes the route harder, right, for a human. So I saw somebody said that on the highest level of climbing, the V17 or 16 or something like that, which is very, very hard, like way beyond. The holes are actually like credit cards, so they're about this thick. So this is your wall, and now, oh, here's your hole. You can grab one there. That's what, this is like when you compete in the Olympics. That's the kind of stuff you do. Huh? Yeah, yeah. Actually, maybe a little bit thicker than this because it's they said a credit card, but a credit card is like what, two of these. So anyway, the thinner the hole, the harder it is. But that turned out not to be true for our robot because the students had just sort of guessed at uh, the hook that they needed. So it was actually very hard for a robot to hang on to these, but it was much easier to hang on to those. And since we don't even have an actuator there, there's no muscle fatigue or running out of battery or anything. There, the robot will just latch on and then it'll just hang there. So it'll be amazing rock climber. Once we get to level V5, we'll be rocking this competition. It's the problem getting from V0 to V5 at the moment. Because the movements that you do, or my feeling is that the movements that you do between V0 and V5 are basically the same. It's just the holds become smaller and smaller. So you need to be stronger and stronger. It's not like they have all of a sudden new movements or something like that. They have a couple of them, I guess, but mostly it's just smaller holes. So smaller holes we can do, we just can't do any climbing at the moment at all. So that was pretty interesting tests that we did there in order to try out things. And then for the assignment, so there's kind of 5 parts, sorry. Humanoid robot design, which you have designed the leg already at the moment, I assume. So you take the top off, and then build the other leg and the torso. Then the rock climbing robot simulation. So in Mujoko, you want to import your robot design, or you can use the Taiwan Bear or the OP3 as your model, and then set up the simulation environment, including the floor, the wall, various climbing holes, and the various robots you want to have. Then route detection, both for the simulation and the real world. So real world would be pictures just like the one that I've just shown you. The pictures will be straight onto the wall, like 90-degree perpendicular to the wall. So you don't need to worry about perspective distortion or something like that. You're not looking at it from an angle. To simplify things a little bit, then the motion planner, which means once you extracted the holes, you need to come up with a plan for how to climb to the top, given the start position. And there, we also simplify things quite a bit. And then it's the actual control of your climbing, both for the simulation and the real robot. And then here is the breakup of the marks. So the physical robot construction is 15 marks that are actually bonus marks. So you can use those to make up for deficiencies in other parts of your coursework. Then the rock climbing robot simulation, 20 marks. Route detection, 30 marks. The motion planning, 30 marks. So those are the 2 big topics, of course. And then plan execution, 20 marks, and another 15 marks bonus for plan execution in the real world. So if you get your real robot to climb. And so then that would be a total of 130 marks. And it will be graded out of 100. So you may get 30 extra marks that you can use for other parts of this assignment or your other coursework. So when we look at trying to detect the holes, and sort of trying to figure out how to use them, I think we will use, or I propose a simple heuristic where the top part of the hole is always our sort of active edge. So we assume that that's where the robot can latch on. And then we also need to have the other part of the hole, simply to avoid the robot hand form or the robot body to bump into it, right? Simply to avoid any collision with it. So then we process the image, we extract the contour, and after you have the contour, you can apply the polyline approximation. So that takes it and breaks it down into line segments. And then the line segments at the top. So this one here, we assume that this is the top edge. And that will be true for most of these holes. If you apply that here, that it wouldn't work for this one. And it wouldn't work for this one and this one. But we don't have those in our test cases. Certainly not at the beginning. Now, for this, what you want to return is A, the position of it, and I would take the position of the active edge because your robot is going to grab there. Otherwise, you would just have to constantly add some offsetting. You can also make a center here if you want to, but then you need to take that into consideration when you calculate the inverse kinematics for your robot. And then you need x and y, which would be, let's say, this position. You would need to know theta, which is the angle here, and I propose that we align it so that this is 0 degrees. This will be negative, this will be positive theta. Just so that, yeah, that we all have the same reference. And then some of them, especially in simulation, if you've looked at a couple of them, you can actually identify them by the type, like these ones here, for example. Right? So you may be able to tell me what type that is. If you have the type, then you can encode more information exactly about how to hold it. Or, for example, this one here. If you encode the type, then you know, oh, I need to look for this edge and I need to push up. I cannot push down. But other than that, that's the, if you don't know the type, then you just return unknown x, y, and theta. So once we have that, then we want to plan a pass through the domain, through the route, and there different types of search algorithms popular for doing that kind of problem. One would be an exhaustive search using heuristics based on A star. The other one would be rapidly exploring random trees. But when we do the motion planning, there's obviously many different types of motions that you could do. So we will limit our rock climbing scenario. I mean, you'd have to plan this, right? That would be pretty out of this world for your robot to consider, I believe. So we simplify it to a ladder style climbing, which is simply saying that we assume that your robot always has three holes minimum that he can grab onto at the wall, which means 2 hands and 1 foot, or 2 feet and 1 hand, most commonly, right? So once you have 4, you can release one of them. So you're in the wall like this, then you let go of this hand. You can use the other 3 to push your center of mass, then you can latch on to the next one. So let's say this looks like this, and then here's another hole. Then you let go of that one, you move your center of mass. Maybe I did it wrong. And then let's copy this. So the idea is that all 3, that you always have 3 points on the wall that you're latching on or you're standing on. That gives you 1 free, then you can move your center of mass, connect there. And then again, now I can maybe lift off this leg, so this leg will move somewhere. Or I can move off this leg and then I can move there. And these ones stay the same. Now at all points, the 3 points that you have that are on the wall form a triangle, and the center of mass of your robot has to be within this triangle all the time as well. So here I let go of that one, so then my thing would be like this. And the center of mass is here somewhere. The center of mass is here, which is within that triangle. And that gives us a little bit more stability for the climb. The problem is if you just have 2 holes or two hands close together and 1 foot, and your center of mass moves over this way, you actually go like an open door or closed door thing. You kind of rotate away from the wall, and then you either have to do another move while you're hanging there, or you fall off the wall. So we don't want that. So it's a very simple climbing strategy. Always 3 holes and the center of mass within that triangle. So that is nice because it severely reduces the search space that you have. Because right now, then your climbing will all be just the sequence of hand and foot holds that you move to. And you can use forward kinematics, inverse kinematics in order to then move the joints to the correct position. So here there's some examples of the rock climbing with the triangle that you have. So there we have the bear, and he's there, and this is our region of stability. This one lets go. We'll move to the top there. Then we have this triangle when I let go of this left foot here. Okay, any questions? Oh, and for the holds, we limit it to 3 types of holds. So they may not all look the same, but basically you can grab them from any angle. This one you must grab with the left hand, leaning this way, and this one you have to grab with the right hand. Which means that your center of mass has to be here, your center of mass has to be to the left of this, here your center of mass has to be to the right of this. So that gives it a little bit more interesting. And then once we can generate plans for that, then we can think about introducing other types of holds. But right now we're limiting ourselves to 3. Now the plan execution in simulation is pretty straightforward, right? You just need to run it through the Mujoko simulator. I do believe there's one thing that you need to be aware of, that you need to think. If your hold is like this, and you want to grab this with your hand, then I think you want to execute that motion a little bit exaggerated. So I would bring the hand up first, and then over, and then down against the wall, somewhere hit the wall here, and then pull it back. Because otherwise, if you have noise in your position control, then and this is the hold you're trying to grab, and you're grabbing it, this is what you want to do. But if you hit exactly this thing and there's a little bit of noise, you may bump into it. So I think you need to be above and then pull it down. Similarly, what the human climber has to do too, depending on whether they can see the hold or not. Actually quite a few of them, you need to be very precise with your motion. I don't think we have one in that picture. It's kind of like this hole, this big green one here. This one is huge, but they also have those in a much smaller version. And then you can bring in 3 fingers if it's a big one, and if in the worst case you can just hold on with 1 finger there, right? And those you have to hit exactly. Like if you're off by, you have to be very precise with your movement there. I don't know if you can climb those, but I always always hit my finger, and then it's like pretty painful. So it's not just that there's nothing there to hold on to. Like you have to do pull-ups like this. It's pretty hard. It's not just that there's nothing there, but even to just get anything, you have to be very precise in your movement. And so, yeah, this should be the output of your vision system, and then the output of your planning system would be a sequence of 1, 2, 3, 4, 5, 6, 7, 8, 9. How you want to climb through the holes. Yeah.
Yeah, I'm thinking about the movement. You told us that we want to reach the position and then do like this. So
If you can, yes.
yeah, is it because I think one problem is when the robot reaches the position or is in the area of the position, will be in front of the
Yeah, yeah,
hole.
sure. It has to get over the hole.
So
Yes.
then our camera will not see the hole.
I don't think we will climb under camera control.
Ah, okay. So this is not.
So this is not done with the camera. Um, I mean, if you want to, we will send the camera feed from the global camera to your robot. But realistically, the positions, if you have those three, you can actually position this quite accurately. Which means that there should be not much noise in the motion.
But how we get the feedback with our camera?
What feedback?
Where our hand is.
You can connect the serial cable to the Pico. So the robot, it's a humanoid robot, but it's specifically we're interested in rock climbing. So I want to make it easier. So the battery we can connect via cable. And the control, you can control it from your laptop with the camera further away. So the Pico will only execute the motions. So I would implement the inverse kinematics of your particular robot on the Pico, and then your laptop or your main controller would just be able to send, like, move the right hand to these XYZ locations relative to your torso. And your robot doesn't need to walk to the wall. So you can start in a position where I'm not sure what the. So the routes that we will test this on are done by the T-Up professional rock climbing gym route setters. So they're all very excited about this. They had a lot of fun with our robot in their gym. But I assume that we will have something like this. 1, 2, 3, 4. So there's some kind of start position that you can get your robot into. There also won't be any dyno movements or anything like that where there's a lot of uncertainty about your position. Your position should be pretty much governed by the commands that you send to the individual joints. And we'll make the holes large enough so that the error is not going to be that detrimental. But yes, if you want to do this, if you want to compete against the Olympic champion, which is something that I think would be really cool, but that'll take a couple of years, maybe 3 to 5 years, before we can do that. Then, of course, you would have to put the camera on board. But then the vision system problem becomes a lot harder because you would need to be able to detect the geometry of the hold from any kind of angle. And so I think that's out of scope. and there's two separate components. So first one is we are um, doing the vision processing. We get the sequence of movements that we need to go through, and then we want to execute those motions. Now, in the simulation, you should have, because you can add additional sensors. So in the simulation, you can actually use the torque feedback. So you could move until you hit the hole, and then you notice that you're pulling something. But the RC servos don't actually have torque feedback. Now, in theory, we could add that, but I'm not sure how useful that will actually be. Because if we use like for our large humanoid, that one actually uses torque feedback and everything, torque control. But with the RC servos, that would be hard to do. So, but yeah, that's how far we got. And no pinching, you don't need any grip or anything like that. Basically, your hands should be just like hooks, like this, so you can hook onto it. And David and Sonic are going to build the climbing wall here with the different holes. So we need to 3D print some holes. Actually, I also think it's okay to just cut them out of styrofoam, but that would be okay. Let me just check here. Well, these are kind of a little bit boring, but yes, we could use those. I uh, I made some different styles, but they're all classified as center, right, and left. So here we have some more. By the way. Hmm. And here, so we can. Hmm. We got some more holes, so I can import those into Blender. So this one, so this is actually a crimp, so I think that one is a little bit too extreme. This is the zero location. So we want to place it there, and then rotate X, oh, X 90 degrees. And this would be the, now we can add a material. So let's make that a blue hold. Okay. Then I want to create a new collection. Center holes. Front. Then I show and this one here and hide it. Oh, it's too big, way too big. Forgot to check the dimensions. So right now it's snap selection to okay, and the scale is correct. This is 152 meters long now, so a little bit too extreme. So scale, scale 0.001, and it's 15 centimeters. 1.5 centimeters. 10 centimeters. Right, then we can hide it. Now I can import the next one. And I'll do two and you can prepare the other ones. So first scale 0.004. Scale 0.004. And let's see what that looks like. Okay. Then rotate X, rotate X minus 90. Rotate Z 180. Snap selection to cursor. Oh, that's the top. That there. Okay. Then maybe I bring that up. Okay. And rotate X. So here we have two separate ones now. Then what we can do is, because I always forget exactly what the commands are. I usually just like to write a Python script attached to my Blender file that does the stuff that I need to do. Okay, no. Our Copilot is now talking to me in Chinese. So if you do some Python programming in Blender, you have noticed that you cannot actually do print on this terminal here. If I run it, I won't actually get any output because it goes to the standard console. But I can copy and paste this. Copy, paste, and then it tells me the two holes that it has. And then in order to incorporate it into Mujoko for these holes, I will need to generate the mesh, and I need to export the Blender file, the Blender object, to a, either object file format or STL file format. So I'm not sure which one would be better. I'll go with object because I think it includes the material, but I haven't actually had a chance to figure out how to get the material in Mujoko, I have to admit. Okay, so let's try that. Object name, object. Okay, then let's see what we get if I export it like that. So here now I have the two holes that I defined and exported. And then let's do a new one. First save as new one, general. And then let's see if I import it. Object. Where is it? Oh, there, yeah. And it actually has the material associated with it. That was the pink one. So now let's see if we can move them into Mujoko. So I can copy them here and then make a wall, see what they look like. So my wall scene with the bear. I think this one is. We have one there. Here's the wall. This is blockchain. Okay. Two. So I can also include those, and they would be. I have to copy them to the. Center hold one, center hold two. Five and six. Now this one, I've rotated them before, so this should actually be 1000 in quaternion. I'm pretty sure. Now we can check. And then this would be. Maybe at that. Now I saved this to root version 2. No. Oh no, there is. Yeah, they're there, but very small. Okay. What happened to this? Oh, I think I was playing around with the gravity. Okay, so that's okay, but no C or Taiwan repairs. made them too small. Assets, wall, center hole 1, center hole 2, and y. Y should be 0. And reload it. No scale. Okay, so where is it now? Yeah. Okay. Ah, yes, that's the thing. If you want to export anything in Blender, then Blender is kind of like Photoshop, so um, it's not destructive. So when I scaled this object, right, it was way too big before I scaled it. It actually, because it's all transformation matrices, so it doesn't actually scale the vertices or the geometry. It just sets a flag saying scale this by 0.0004, which if I print it out, it's just 0. So now when it's trying to plot it, it'll actually take this geometry though. So I need to go Control A, apply, and then apply the scale. So now it actually scales the entire geometry. So now it'll change the position of the vertices. Before, the vertices remain unchanged. If I hit Control Z, all it has to do is reset the scale to 1 and it'll plot it in the original size. Now, if I say scale it to 1, it'll be this size. I always forget to do that. And here, Control A, scale, apply the scale. So now our scale is 1, 1, 1, 1, 1. All once. Then I can save it. Then I go wall. Then I go 10. And which one is this? That's the file files. And now it's still good. Uh, It's in there. One is there, the other one will be there. So I need to bring them further out. Four, four, two, three. And then everything is okay. I think, no. Oh, so that's one of the problems with the export. Uh, the blender uses that goes up. Most of the game engines use that going out of the camera and going forward. So uh, that's one difference, and that was one of the arguments. And the other problem is, I believe it exports the same thing twice. And I still don't know how to get the colors. So I go up axis is that. My modifiers, true, export, forward axis. Is equal to y, negative 1. And does it do selected? Backup image move from volume. Okay. Okay. So let's see if I load it. Okay. And import. No. And it exports the same thing twice. Now let's look at the sizes. No, it's the same. Hmm? That's a bit confusing. Ah, yeah, 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 So let's see if I run this. Mm, both of my robots. Oh, there it is. Okay. And there. So now I got the position, but it only exports one. And it doesn't get the color for some reason. This one is also really small. If I go here and export, maybe I need to load this PDR expansion. Novels. Center hole 2. This is not even really full. Not really, no, it's supposed to be that way. I want to find the other one. There should be a second one. But the problem is every time I run the Python script, it only exports one. So when I get two that are the same. So now what do I have? Now I have two different ones. Uh, oh, this went to mains. Yeah, more import, export. Okay. Can we hit that move? Maybe I can. You can turn on some stuff for the visualization. So here you can take the body, so it's there. So let's scale it up a little bit so we can find it. Oh, it's the wrong geometry. I have two there. Center hole 2, 6 center, 1.6, and let's put it straight in the middle. No, yeah. It's just hard to see on that wall unless I make it larger. It's not very big. So now it's there. Then let's bring it close to here. Oh, there. Yeah. So these are the two. It's just hard to see because it's gray. And for some reason, even though when I import it um, into Blender, it shows the color, but Mujoco doesn't seem to be able to do that. So I can change the color here. 1101, and then we should get a nice yellow. Okay, and then RGBA is equal to 0, 1. Ah, okay, finally I have it. Okay. So you can generate then arbitrary test images for your vision algorithm. You can just put them into Moodle. Just want to make sure this still works. And I'll push that to the GitHub repository just in case you want to play with it some more. Good. Okay, good. Then I think that's it for today to get you started on the assignment. Um, extend the roots, put some more holes in it, like I have with the road 1 and road 2 in the GitHub repository, and then you can start working on your vision system, and we will take some more pictures of real roots that you can use in order to extract the holes, which will be a bit more challenging, but since you're given uh, the crop version, a small cutout of the image, that'll allow you to actually get a pretty good color calibration to begin with, I think. And so you have your partner. You guys finished building the humanoid robot as well. You finished building the humanoid robot? No, no. Yeah. What? No, you should start working on finishing. Yeah, yeah. A question related to that actually, just because the plastic board is always the strongest, especially in the direction that it folds. Can we I saw that a 3D printer in the lab. Can we use that 3D printer? Yeah, we can use the 3D printer. We have one in the lab. You need to talk to David and Sonic. Yeah. Okay, I can talk to you. We can use it. Yeah. Mhm. Um, yeah, I don't expect that everybody uses the 3D printer. I mean, the corrugated cardboard that you guys were using is very weak, right? If you wanted to use that, at least you would have to make it an edge, like bend it so that you have at least this part, or make it a tube or square. Something like that. That would work already. If you have a 3D printer design, then you can do that too.
But it's
Wood is okay too, yeah.
that's true.
But you don't know, for climbing, the bending may be better actually, because you don't need to be so precise. You have a little bit more flexibility.
Precisely.
If you build it very strong, you have to be very precise. Right?
Yeah.
If you have a little bit of give in it, then if you hit it, it may pop up and move over and get in. But yes, so yeah, that is good. Yeah. Again, the point is not to compete with Unitree. To build a small humanoid, but yes, we can. David can get you access to the 3D printer. That would be the more modern approach for sure. I'm just old school still. Okay, good. Then that's the end of the class for today. Yeah. And then also get it off this one here. Even though this one has no sound, this one has just video. It's in this computer. Those are the two from today, and we will have to